Far out in the deep universe, motion is constant, yet almost nothing ever touches. Entire galaxies drift through space at hundreds of kilometers per second, guided by gravity across distances so large they resist intuition. Over billions of years, these vast systems slowly approach one another, their shapes stretching, their stars rearranging, their futures quietly rewritten. From a distance, the event looks dramatic. Spirals twist. Long streams of light arc outward. Two luminous forms seem destined to crash. But up close, something unexpected happens. Stars pass by stars without contact. Planetary systems remain intact. No great wave of destruction sweeps outward. What unfolds instead is a long, gentle reshaping of structure driven, not by impact, but by gravity acting patiently over time. A collision that is not a crash, a merger that unfolds in near silence. This is one of the strangest truths in astronomy. The largest collisions in the universe are also some of the calmest. They take place in near vacuum, stretched across timescales far longer than any civilization, any species, or any single star could experience directly. From within a galaxy, the night sky would change so slowly it might never feel like an event at all. Tonight, the focus is not on explosions or chaos, but on scale, emptiness, and motion, on how structure evolves when almost everything is space, on how the universe transforms itself without force, without noise, and without anything ever really touching. So, welcome. If you enjoy calm, thoughtful journeys through science, you're in the right place. Take a moment to like this video and subscribe to the channel, it truly helps. And as you settle in, feel free to share where you're watching or listening from tonight. Let's begin. A collision is usually imagined as a moment of contact. Two cars meet at a junction, a ball strikes a wall, something moving encounters something solid, and the result is noise, force, and sudden change. In everyday life, collisions are sharp events. They happen quickly, they leave marks. They are defined by impact. That expectation follows naturally from life on Earth, where matter is dense and distances are small. Rooms have walls, roads have edges, objects tend to be close together. An empty space is something that exists only briefly between one surface and the next. In that setting, a collision without contact sounds like a contradiction, almost a trick of language. Out in the universe, the same word means something very different. At cosmic scales, a collision does not need contact. It does not require surfaces to meet or objects to strike one another. Instead, it describes a long process of interaction guided almost entirely by gravity, unfolding across distances so large that impact becomes almost irrelevant. When astronomers speak about galaxies colliding, they are not describing a crash in the everyday sense. They are describing two vast systems passing through the same region of space and slowly reshaping each other as they do. The key to understanding this difference lies in emptiness. A galaxy appears solid in photographs. Its spirals glow. Its core shines brightly. From a distance, it looks like a crowded, luminous structure packed with stars. But that appearance is deceptive. A galaxy is not a solid object. It is a gravitational system held together by mass and motion, in which almost all of the volume is empty space. Consider a single star system like the one surrounding the Sun. The Sun itself occupies a region a little over 1 million kilometers across. The nearest planet orbits tens of millions of kilometers away. Beyond that, the outer planets drift billions of kilometers from the center. Even within this small corner of the galaxy, space dominates. If the Sun were reduced to the size of a grain of sand, Earth would orbit several meters away, and the nearest star would be thousands of kilometers distant. That pattern repeats on larger scales. Stars within a galaxy are separated not by meters or kilometers, but by distances measured in light years. Even in relatively dense regions, the typical separation between stars is vast. There are places where stars cluster more tightly, such as globular clusters. Yet even there, collisions between stars are rare over the lifetime of the universe. This is why the phrase "without touching" is not poetic language. It is a literal description. When two galaxies approach each other, their stars do not behave like particles in a collision chamber. They do not slam together or shatter. Instead, they continue along their paths, guided by gravity, slipping past one another with enormous distances still separating them. The probability of one star directly striking another during a galactic merger is so small that for most purposes it can be treated as zero. This idea was unsettling even to early astronomers. When galaxies were first recognized as systems beyond the Milky Way, there was a natural tendency to imagine them as enormous star clouds that would collide violently if they met. Over time, careful observation and theoretical work showed otherwise. The universe, it turned out, is far emptier than intuition suggests. Gravity changes everything. A galaxy is not held together because its stars are close. It is held together because gravity acts across distance. Every star, every cloud of gas, every grain of dust contributes to a gravitational field that extends far beyond what can be seen. This means that two galaxies can begin influencing each other long before they appear to meet. Their shapes stretch, their motions shift. Long streams of stars can be pulled outward into space, tracing arcs that last for hundreds of millions of years. None of this requires contact. Instead of impact, the dominant process is interaction. Orbits change, paths bend, energy is redistributed slowly and gently. The changes are real, but they are gradual, unfolding over spans of time that make sudden violence impossible. To anchor this in scale, it helps to step back even further. A typical galaxy contains hundreds of billions of stars. Yet, the combined volume of all those stars occupies only a tiny fraction of the galaxy's total size. If all the stars in a galaxy were compressed together, the resulting object would still be minuscule compared to the space the galaxy normally fills. Most of a galaxy is simply room for motion. This is why two galaxies can pass through each other and remain recognizably intact for long periods. Their stars weave through overlapping gravitational fields like two swarms of insects crossing paths in open air. The swarms influence each other's motion, but individual members rarely collide. There is quiet humor hidden in this idea. The largest structures in the universe participate in collisions that are defined by not touching. The word remains the same, but the meaning shifts entirely. What feels contradictory at human scale becomes inevitable at cosmic scale. Scientific bodies, such as space agencies and observatories, have confirmed this picture repeatedly through observation and simulation. Detailed computer models built using the laws of gravity and informed by telescope data show galaxies approaching, overlapping, and merging without widespread stellar destruction. These simulations match what is seen in real systems scattered across the observable universe. The long tails, warped shapes, and stretched arms tell the same story again and again. Even the word empty needs care here. Space is not nothing. It contains gas, dust, radiation, and unseen mass that reveals itself only through gravitational effects. But compared to the density of everyday objects, it is astonishingly sparse. This sparseness is what allows motion without impact, change without collision in the usual sense. Thinking this way requires letting go of familiar instincts. The mind expects collision to involve contact because that is how the world behaves at human scale. At galactic scale, those instincts mislead. The universe operates under the same physical laws everywhere, but the outcomes look different when distances stretch and densities fall. Once this shift in perspective settles in, the phrase "when galaxies collide without touching" stops sounding strange. It becomes a precise description of a process shaped by scale, probability, and gravity rather than forceful impact. It describes a universe where interaction is subtle, patient, and continuous, where enormous changes arise not from crashes, but from slow rearrangements of motion. This reframing matters because it clears away misconceptions before anything more detailed is explored. Without it, later descriptions of mergers, star formation, and structural change would seem contradictory or incomplete. With it, the story of galactic interaction becomes coherent, grounded, and surprisingly calm. The universe is not built from constant collisions. It is built from motion through space that is mostly empty, guided by gravity acting quietly across immense distances. Understanding that simple fact reshapes how everything else is seen, from the movement of stars to the evolution of galaxies themselves. To understand what happens when galaxies interact, it helps to pause and ask a quieter question first. What is a galaxy really, when stripped of its glow and its familiar shapes? What is actually there, moving through space, responding to gravity and slowly changing over time? A galaxy is not a single object. It is a layered system built from several very different ingredients, each behaving in its own way. Together, they form a structure that can be stable for billions of years, yet flexible enough to be reshaped by encounters with others like it. The most obvious component is stars. These are the parts that dominate photographs and capture attention. Hundreds of billions of stars can orbit within a single large galaxy, each producing light through nuclear fusion at its core. Stars give galaxies their color, their spiral arms, and their bright central regions. They also provide the reference points by which galaxies are classified and compared. Yet stars, for all their brilliance, are not the bulk of a galaxy in either volume or mass. They are bright markers embedded in something much larger and far more diffuse. Between the stars lies gas. This gas is mostly hydrogen with smaller amounts of helium and trace elements forged inside previous generations of stars. In some regions, it is cold and thin, drifting quietly through interstellar space. In others, it is compressed and heated, glowing faintly or collapsing to form new stars. Gas is the raw material of future stellar generations, and it plays a central role in how galaxies change over time. Mixed into this gas is dust. Despite the name, cosmic dust is not like household dust. It consists of tiny solid grains made of carbon, silicon, oxygen, and heavier elements. These grains absorb and scatter light, shaping how galaxies appear when observed. Dust lanes trace spiral arms. Dust clouds obscure stellar nurseries. Although dust contributes very little mass, it has an outsized effect on appearance and behavior. Together, stars, gas, and dust make up what is often called the visible galaxy. This is the part that telescopes detect directly. It is also the part that feels most tangible. But even combined, these components account for only a fraction of what a galaxy truly contains. The largest contributor to a galaxy's mass is something that cannot be seen at all. Dark matter does not emit light, absorb light, or reflect light. Its presence is known only through its gravitational influence. When astronomers measure how fast stars orbit within galaxies or how galaxies move within clusters, the visible matter is not enough to explain the motion. Something else must be there, providing additional gravity. This unseen component forms an enormous halo around each galaxy, extending far beyond the visible stars and gas. The dark matter halo acts like a scaffold, shaping how galaxies form and how they hold together. Without it, galaxies as they are observed could not exist. With it, their motions make sense. The exact nature of dark matter remains unknown, but its role in galactic structure is well established. In terms of mass, it outweighs stars and gas by a wide margin. Most of what a galaxy is made of never appears in images at all. At the center of many galaxies lies another remarkable feature, a supermassive black hole. These objects contain millions or billions of times the mass of the Sun compressed into a region smaller than a planetary system. Despite their reputation, they do not act like cosmic vacuum cleaners. Their influence is strongest nearby, shaping the motion of stars and gas close to the core. Central black holes are linked to the evolution of their host galaxies in subtle ways. As gas falls inward, energy is released. Jets and radiation can affect star formation across large regions, although the black hole contributes little to the overall mass compared to dark matter. It plays a key role in regulating activity at the galaxy's heart. When all these pieces are considered together, a galaxy becomes something very different from a glowing object drifting through space. It is a dynamic system. Light marks only a small fraction of what is present. Gravity binds everything together, extending far beyond what the eye can see. This understanding helps explain why galaxies come in different shapes. Spiral galaxies, with their winding arms and rotating disks, are often rich in gas and actively forming new stars. Their structure reflects a history of relatively gentle interactions and sustained rotation. Elliptical galaxies, by contrast, are smoother and rounder, with stars moving in more random orbits. They tend to contain less cold gas and show little new star formation. Irregular galaxies lack a clear shape altogether. They may be small, distorted, or disrupted, often as a result of past interactions or ongoing gravitational influence from larger neighbors. These categories are not fixed identities, they are outcomes. A spiral galaxy can become an elliptical one. An irregular galaxy can settle into a more ordered form. The shape a galaxy has at any moment reflects its past, not a permanent label. Early in the 20th century, astronomers were only beginning to piece this together. Edwin Hubble played a major role by systematically observing and classifying galaxies based on their appearance. His work helped establish that galaxies are separate systems beyond the Milky Way and that their shapes follow recognizable patterns. Hubble's classification scheme was never meant to suggest an evolutionary ladder, but it provided a useful language. Over time, as observations improved and theoretical understanding deepened, it became clear that interactions and mergers could move galaxies from one category to another. The shapes were snapshots, not destinies. One of the most counterintuitive aspects of all this is how little space stars actually occupy. Despite their numbers, stars are tiny compared to the distances between them. Even in a galaxy packed with hundreds of billions of stars, most of the volume is empty. The luminous parts are like scattered embers in a vast, dark field. This is why a galaxy can be massive without being crowded. It is also why gravity, not contact, governs galactic behavior. Stars orbit within gravitational fields shaped largely by dark matter. Gas flows respond to pressure and attraction. Dust drifts and absorbs light. Black holes influence their surroundings quietly and persistently. Seen this way, a galaxy is less like a solid object and more like a slow-moving ecosystem. Matter circulates, energy flows, structures form, dissolve, and reform over time. Light provides hints, but gravity tells the deeper story. Grounding the idea of a galaxy in this physical reality matters. Without it, interactions between galaxies seem confusing or contradictory. With it, those interactions become understandable consequences of how mass and space are arranged. What moves during a galactic encounter is not a solid body, but a layered system dominated by emptiness, guided by unseen mass, and marked by points of light that occupy only a tiny fraction of the whole. Once that picture settles in, the behavior of galaxies begins to feel less dramatic and more inevitable, shaped by structure rather than spectacle. A galaxy is not what it looks like at first glance. It is what holds together, what extends beyond sight, and what responds patiently to gravity over immense spans of time. The most important feature of a galaxy is not what shines, but what lies between the points of light. From Earth, the night sky gives the impression of closeness. Stars appear sprinkled across a dark surface, separated by tiny gaps. Constellations form shapes that feel compact and familiar. This impression is comforting, but it is deeply misleading. The true distances between stars are so large that the word gap barely applies. Take the nearest star beyond the Sun. Even our closest neighbor sits more than 4 light-years away. That distance is so large that light moving faster than anything else in the universe takes over 4 years to cross it. Nothing about everyday experience prepares the mind for separations like that. To make this easier to picture, imagine shrinking the Sun down to the size of a small marble. At that scale, Earth would orbit several meters away. The outer planets would be spread across a space the size of a neighborhood, and the nearest star would not be in the same city or even the same country. It would be thousands of kilometers away. Between those two marbles, there would be nothing at all. That emptiness is not an exception. It is the rule. Galaxies contain hundreds of billions of stars, yet they are spread across regions tens or hundreds of thousands of light-years wide. Even in the bright spiral arms where stars are more common, the average separation remains immense. Most of the volume of a galaxy is simply space where nothing solid exists. This is the key reason galaxies can pass through one another without stars colliding. When two galaxies overlap, their stars do not suddenly become crowded. They continue to occupy roughly the same relative distances they had before. The space between stars in one galaxy is still vast, and the stars from the other galaxies slip into those gaps with ease. It is not that collisions are rare, It is that they are almost unthinkable. The idea of a stellar collision sounds dramatic, but it is statistically negligible. Even during a direct galactic overlap, when billions of stars share the same region of space, the chance of one star striking another remains vanishingly small. Astronomers can run simulations that track millions of stellar paths during mergers and still find essentially no direct impacts. This comes down to simple probability guided by separation and size. Stars are tiny compared to the distances between them. A typical star is a few million kilometers across. The space between stars is measured in trillions of kilometers. When objects are that small relative to their spacing, direct contact becomes extraordinarily unlikely. It is the difference between throwing 2 handfuls of sand into the open ocean and expecting the grains to collide. Density matters here, but even the densest stellar environments remain mostly empty. Star clusters are often cited as crowded places, and in relative terms they are. In globular clusters, hundreds of thousands of stars can be packed into a region only a few dozen light-years across. Compared to the rest of a galaxy, this is dense. Compared to everyday standards, it is still almost entirely void. Even in these clusters, stars are typically separated by distances far greater than the size of their planetary systems. Collisions can happen there, but they are rare events spread across billions of years. They are notable precisely because they are exceptions. This helps explain why galaxy collisions do not produce chains of stellar impacts. When 2 galaxies merge, their densest regions overlap briefly, then drift apart again. The time spent in close proximity is short compared to the enormous distances involved. The stars simply do not have the opportunity to meet. There is a quiet irony in this. Galaxies are sometimes described as crowded cities of stars, yet they behave more like rural landscapes stretched across cosmic scales. Everything is connected by gravity, but nothing is close. The mind often tries to picture galactic overlap as 2 clouds of blowing matter slamming together. A more accurate image is 2 intricate lace patterns sliding through one another without tearing. The patterns distort, threads stretch, but the spaces between threads remain dominant. Astronomers have confirmed this picture by studying galaxies caught mid-merger. Long tidal tails stream outward. Spiral arms twist and warp. Yet individual stars continue along smooth paths, largely unaffected by the presence of foreign neighbors. The violence is visual, not physical. Even when stars pass relatively close to one another, gravity softens the encounter. Their paths bend slightly, orbits shift, but contact remains unlikely. Space gives them room to mess. This vast emptiness also explains why planetary systems are generally safe during galactic mergers. Planets orbit stars on scales that are tiny compared to interstellar distances. As stars pass by other stars, those encounters are usually too distant to disrupt planetary motion. A solar system could travel through the heart of another galaxy and remain intact, unaware that anything unusual is happening beyond a slowly changing night sky. There is gentle humor in how counterintuitive this all feels. On Earth, more objects in one place means more collisions. In space, adding billions of stars barely changes the odds. Scale reverses expectation. Scientific institutions that model galactic evolution rely heavily on this emptiness. Their simulations assume that stars can be treated as points moving through a smooth gravitational field, rather than as objects that strike one another. When these models reproduce real galaxies with striking accuracy, it reinforces the same conclusion. The universe is sparse to a degree that defies instinct. Understanding this sparseness is essential. Without it, the calm nature of galactic mergers makes little sense. With it, the idea of galaxies interpenetrating becomes not just plausible, but inevitable. Galaxies are vast because space allows them to be. Their stars shine because they are isolated, separated, and stable. When galaxies meet, they do not become crowded. They remain what they always were, immense collections of light suspended in an ocean of emptiness. Once this is absorbed, the phrase "without touching" loses its mystery. It becomes a straightforward description of how nature behaves when distances grow large and matter grows rare. At these scales, space itself becomes the dominant feature. shaping everything that follows. If stars rarely touch and matter is spread so thinly, it raises a natural question. How can galaxies affect one another at all? What reaches across those immense gaps and produces the dramatic shapes seen in merging systems? The answer is gravity. Gravity does not require contact. It does not fade at the edge of an object. It extends outward endlessly, growing weaker with distance but never truly disappearing. In a universe where space dominates and matter is sparse, gravity becomes the primary way objects communicate. At everyday scales, gravity feels subtle. A falling object accelerates quietly toward the ground. The pull between two people standing side by side is real, but far too small to notice. At cosmic scales, however, gravity governs everything that moves. It shapes the paths of planets, the structure of stars, and the behavior of entire galaxies. The earliest clear description of gravity comes from Isaac Newton, who showed that every mass attracts every other mass. In Newton's picture, gravity acts instantaneously across space, pulling objects together in proportion to their mass and distance. This framework works remarkably well for understanding the motion of planets and stars, and it remains useful for many astronomical calculations. Centuries later, Albert Einstein refined this picture with the general theory of relativity. Instead of gravity being a force that reaches across space, Einstein described it as a curvature of space and time themselves. Mass tells space how to curve, and curved space tells matter how to move. The result is the same familiar attraction, but understood at a deeper level. For galaxies, the distinction between these views matters less than the shared conclusion. Gravity acts across enormous distances. It does not stop at the visible edge of a star or galaxy. Its influence extends far beyond what telescopes can see. This is why galaxies begin interacting long before they appear to touch. As two galaxies approach each other, their gravitational fields overlap. Stars feel a gentle tug. Gas clouds shift slightly. Entire orbital patterns adjust over time. These effects accumulate slowly, reshaping both systems without any need for physical contact. It helps to imagine gravity as a conversation carried out across space. Nothing needs to collide for the message to be received. Mass alone is enough. This reach is especially important because most of a galaxy's mass is not concentrated in its bright center. Instead, it is spread throughout a vast halo dominated by dark matter. These halos extend far beyond the visible stars and gas, overlapping early during an encounter. Long before spiral arms cross, the deeper gravitational structures are already intertwined. As galaxies draw closer, gravity begins to stretch them. This stretching produces what astronomers call tidal forces. Tides occur whenever gravity pulls more strongly on one part of an object than another. On Earth, tidal forces from the Moon and the Sun gently raise and lower the oceans. In galaxies, the same principle operates on a much grander scale. When a galaxy enters the gravitational field of another, stars on the nearer side feel a slightly stronger pull than stars on the far side. Over millions of years, this difference elongates the galaxy. Spiral arms can be drawn outward. Long streams of stars can be flung into space, forming luminous arcs that trace the galaxy's past motion. These tidal features are not signs of impact. They are signatures of gravity working patiently over time. The timescales involved are essential to understanding why this process feels calm rather than violent. Galactic interactions unfold over hundreds of millions or billions of years. Each individual star responds slowly, adjusting its orbit bit by bit. There is no single moment when everything changes at once. Instead, the galaxy flows into a new shape, guided by gravity's persistent influence. There is a subtle beauty in this slowness. At human scale, change often comes through force and contact. At galactic scale, change comes through gradual rearrangement. Gravity reshapes without striking. It sculpts rather than shatters. This is also why galaxies can survive repeated encounters. A galaxy may experience multiple close passes with others over its lifetime, each one leaving a mark without destroying the whole. The structure evolves, but the system remains coherent. Observations from major astronomical institutions support this picture. Telescopes operated by space agencies and research observatories have captured countless interacting galaxies, revealing the same gravitational fingerprints again and again. Long tidal tails, distorted disks, and warped shapes all point to gravity acting across distance, not matter colliding at speed. Even the most dramatic-looking mergers tell this story. What appears chaotic in images is often the result of simple gravitational rules applied patiently over vast spans of time. The complexity arises not from violence, but from many small influences accumulating. This perspective reframes what it means for galaxies to collide. The word collision suggests impact, resistance, and sudden force. In reality, galactic collisions are better understood as episodes of gravitational negotiation. Each system adjusts to the presence of another, exchanging energy and momentum through the invisible geometry of space. The humor, if there is any, lies in how misleading appearances can be. Two galaxies may look like they're crashing into one another, yet their stars are gliding through an expanding web of gravitational influence, barely aware of their neighbors, except through the slow bending of their paths. Once gravity is recognized as the true agent, the earlier ideas about emptiness fall into place. Space can be vast and matter sparse, yet interaction remains inevitable. Gravity bridges the gaps that matter leaves behind. This is the quiet engine behind every galactic encounter. No contact is required. No explosions are necessary. Gravity alone is sufficient to bring enormous systems together, reshape them, and guide them toward new forms over time. Understanding this allows the idea of a collision without touching to feel not just possible but natural. In a universe built on gravity and scale, influence does not need impact. It only needs time. There is a hidden architecture to every galaxy, one that does not glow, does not cast shadows, and does not announce itself directly. Yet without it, galaxies would fly apart, mergers would not unfold as they do, and the universe would look nothing like it does. This invisible framework is known as dark matter. Dark matter earned its name not because it is sinister or mysterious by intention, but because it does not interact with light. It neither shines nor absorbs nor reflects. Telescopes cannot see it directly. Its presence is inferred through motion, through the way visible matter behaves as if something unseen is guiding it. If stars were the only source of gravity in a galaxy, their motion would follow a simple pattern. Stars near the center would orbit quickly, held tightly by concentrated mass, while stars farther out would move more slowly, much like the planets in the solar system. But when astronomers measured how stars actually move, they found something unexpected. Stars far from galactic centers were orbiting just as fast as those closer in. According to visible matter alone, they should have been flung into space. This discrepancy was not subtle. It was consistent, persistent, and widespread across many galaxies. One of the scientists who played a crucial role in understanding this was Vera Rubin. By carefully studying galaxy rotation curves, which describe how orbital speed changes with distance from the center, she helped demonstrate that galaxies contain far more mass than can be accounted for by stars and gas alone. Her work showed that something unseen must be present, extending well beyond the visible edges of galaxies. That unseen mass is now understood to form a vast halo around each galaxy. This halo is not a thin shell or a neat boundary. It is a deep, diffuse structure that can extend several times farther than the luminous stars and gas. Within this halo, visible matter moves, responds, and settles. In terms of mass, dark matter dominates. For a typical large galaxy, the majority of its gravitational influence comes not from the stars that define its shape, but from this invisible component. The stars are passengers riding within a much larger gravitational vessel. This has profound consequences for galactic collisions. When two galaxies approach one another, it is their dark matter halos that meet first. Long before spiral arms overlap or cores draw near, these halos begin to interpenetrate, their gravitational fields merging, creating a combined environment that reshapes the motion of everything inside. From the perspective of visible matter, this invisible interaction sets the stage. Stars respond to changes in the gravitational landscape. Gas flows along new paths. Entire galactic disks can tilt, stretch, or warp as the underlying structure shifts. The collision, in other words, begins when nothing can be seen. This is one reason why galaxies can appear to influence each other at surprising distances. Long before any visible contact, subtle distortions appear. Streams of stars may be drawn outward, rotation patterns change. These early signs reflect the meeting of dark matter halos rather than the interaction of luminous matter. The idea that most of a galaxy is invisible can feel unsettling at first. It challenges the instinct to trust what is seen. Yet the evidence is strong, supported by decades of observation and analysis from astronomical institutions around the world. Computer simulations make this even clearer. When researchers model galaxy mergers using only stars and gas, the results do not resemble real galaxies. The structures fall apart too easily. The shapes do not match observations. The timing feels wrong. Something essential is missing. When dark matter halos are included, everything changes. With dark matter present, simulated galaxies behave like real ones. They form realistic spiral arms. They develop tidal tails that match those seen in telescopes. They merge on timescales consistent with observation. The invisible mass provides the gravitational glue and guiding structure needed for the system to evolve correctly. These simulations rely on well-tested physical laws, applying gravity across millions of particles representing both visible and invisible matter. The fact that they reproduce observed galactic behavior so successfully is one of the strongest arguments for the role of dark matter in cosmic structure. There is a quiet elegance in this arrangement. The most important component of a galaxy is the one that does not announce itself. Light draws attention, but gravity does the work. During a merger, the overlapping dark matter halos deepen the combined gravitational well. This affects how quickly the galaxies lose energy and spiral toward one another. It influences whether the final result is a smooth elliptical galaxy or a distorted remnant still forming stars. It even affects how central black holes eventually find one another. All of this happens without contact, guided by mass that cannot be seen. The humor, if one can call it that, lies in how backwards this feels. The brightest parts of a galaxy are not its backbone. The glowing stars are decorative compared to the dark scaffolding that holds everything together. The collision of galaxies is therefore shaped primarily by something invisible, something known only by its effects. This does not mean dark matter is mysterious in every sense. Its gravitational behavior is well understood. What remains unknown is its exact nature, what it is made of at the particle level. Yet for understanding galactic collisions, its role is clear. It provides the extended reach of gravity that allows galaxies to sense one another long before they meet. In this way, dark matter extends the ideas already introduced about gravity acting across emptiness. It explains how that gravitational influence is structured and sustained. It turns gravity from a simple force into a vast, layered field that shapes motion on the largest scales. When galaxies collide without touching, it is their dark matter halos that truly collide. The visible stars and gas follow along, tracing patterns written by an unseen hand. The encounter unfolds, not as a clash of objects, but as a slow reconfiguration of invisible mass guiding luminous matter into new arrangements. Understanding this hidden structure completes an important part of the picture. Emptiness allows galaxies to pass through one another. Gravity allows them to interact. Dark matter determines how that interaction unfolds. Together, these elements explain why galactic collisions look dramatic, yet remain calm, why change is profound yet gradual, and why the most influential part of the process remains forever out of sight. Up to this point, stars have dominated the picture, and, for good reason. They are the most visible parts of a galaxy, the points of light that define its shape and draw the eye. Yet when galaxies pass through one another, stars behave almost politely. They keep their distance. They adjust their paths gently. They rarely, if ever, collide. There is, however, one component of a galaxy that does not have the luxury of such wide personal space. That component is gas. Unlike stars, gas is not compact. It does not occupy neat, well-defined orbits as individual objects. Galactic gas exists as sprawling clouds, filaments, and diffuse regions that can stretch across hundreds or thousands of light years. It fills much more of the space between stars, even though it contributes far less mass overall. And because of this spread-out nature, gas behaves very differently when galaxies interact. When two galaxies approach each other, their stars pass through overlapping space with ease. Gas clouds do not. They encounter other gas clouds, and when they do, something finally makes contact. Gas cannot simply pass through gas without consequence. As clouds from one galaxy meet clouds from another, they begin to compress. Motion slows, energy builds, the gas heats up. Instead of gliding past, the material bunches together, thickening and changing state. This is where the calm, near-invisible interaction of stars gives way to something more active. The process is not explosive in the cinematic sense, but it is transformative. As gas compresses, it forms regions of higher density. Pressure rises, heat increases. In some places, the gas becomes hot enough to glow, emitting light that telescopes can detect. In others, the compression sets the stage for collapse, where gravity finally gains the upper hand and begins pulling material inward. These compressed regions are the seeds of new stars. Galactic mergers are therefore often associated with bursts of star formation known as starburst regions. These are areas where stars are born at rates far higher than usual, sometimes dozens or hundreds of times faster than in calm galaxies. The collision does not destroy stars, it creates new ones. This is one of the great ironies of galactic interaction. The same event that distorts and reshapes galaxies also lights them up with fresh stellar activity. Observations from major space-based and ground-based observatories have made this clear. Images captured by the Hubble Space Telescope reveal bright knots of star formation in interacting galaxies, especially along distorted arms and tidal features. These regions glow blue, indicating young hot stars that formed recently from compressed gas. At longer wavelengths, observatories, such as ALMA, the Atacama Large Millimeter Array, peer through dust and trace cold molecular gas directly. These observations show dense gas reservoirs piling up in merging systems exactly where theory predicts they should. Where gas concentrates, stars soon follow. This behavior highlights a crucial contrast between stars and gas. Stars are effectively collision-proof because they are small and widely spaced. Gas clouds, by contrast, are large and diffuse. They overlap easily. When they do, their particles interact, exchanging energy and momentum. The result is friction, heating, and compression processes that simply do not occur for stars passing through one another. This makes gas the true site of interaction during a galactic merger. The idea of shock fronts helps clarify what is happening even without technical language. When two streams of gas meet at high relative speed, neither can continue unimpeded. Instead, a boundary forms where motion slows abruptly. Energy that once existed as movement is converted into heat. The gas becomes hotter, denser, and more turbulent. These shock regions ripple through the merging galaxies, reshaping their internal structure. Gas that once drifted quietly can be driven inward toward galactic centers feeding star formation or even central black holes. Other gas is flung outward into extended streams, enriching intergalactic space. The entire process unfolds slowly by human standards, but it is decisive by galactic ones. Importantly, gas makes up only a small fraction of a galaxy's total mass. Yet, its influence during mergers is outsized. Gas determines when new stars form. It controls how brightly a merging galaxy shines. It influences how quickly the system settles into a new shape. In this sense, gas acts as the mediator between gravity and light. Gravity sets the stage. Dark matter provides the structure. Stars trace the motion. But gas responds actively, transforming energy into visible change. There is also an element of feedback involved. Newly formed stars do not remain quiet. They emit radiation. They produce stellar winds. Some eventually explode as supernovae. These processes inject energy back into the surrounding gas, heating it and sometimes pushing it outward again. Star formation can therefore regulate itself, turning on and off in waves. This feedback helps explain why starbursts are intense but temporary. A merger can trigger a surge of star formation, but it does not continue indefinitely. Gas is consumed, heated, or dispersed, and the system gradually settles. Throughout all of this, the contrast with stellar behavior remains striking. While gas collides, compresses, and transforms, stars remain largely unaffected by direct contact. They follow new orbits shaped by gravity, but they do not feel the heat or pressure of the gas around them. From the inside of a galaxy, the consequences would be subtle. Over millions of years, the sky might brighten slightly as new stars form. Nebulae might become more common, yet nothing would feel like a collision. The drama unfolds on scales and timescales far removed from individual experience. There is a gentle humor in this arrangement. The component that looks insubstantial, thin, and ghost-like in images is the one that actually interacts. The bright, solid-looking stars are the ones that pass through untouched. By identifying gas as the place where interaction truly happens, the picture of galactic merges becomes more complete. The calm passage of stars explains why destruction is rare. The active response of gas explains why change still occurs. Galaxies do not collide by smashing their stars together. They collide by compressing their gas, lighting up their interiors, and quietly reshaping themselves from the inside out. In a universe defined by emptiness, it is this thin, drifting material that finally makes contact and leaves the most visible mark. Understanding the role of gas resolves another apparent contradiction. How can galaxies pass through one another without touching yet emerge transformed? The answer lies in recognizing that not all components behave the same way. Some glide, some collide, and it is the colliding component, light and diffuse though it may be, that writes the most dramatic chapters of galactic change. One of the quiet reasons galactic collisions feel so calm is that they unfold on timescales the human mind was never built to grasp. On Earth, events are measured in seconds, minutes, and years. Even the longest processes most people encounter fit comfortably within a single lifetime. Mountains rise and erode over millions of years, but those changes are inferred rather than experienced. Weather shifts in hours. Civilizations rise and fall over centuries. History feels long when it stretches back a few thousand years. Galactic mergers operate on a completely different clock. When two galaxies begin to interact, the process typically spans hundreds of millions to billions of years. The first gravitational influence may begin long before the galaxies appear close together. Subtle distortions build slowly. Orbits adjust. Gas begins to drift. Long before there is anything recognizable as an overlap, the merger has already begun. From start to finish, a full merger can take longer than many stars live. Massive bright stars burn through their fuel quickly, shining for only a few million years before ending their lives. Smaller stars like the Sun persist for billions of years. Some of the smaller stars will outlive the current age of the universe. Against this backdrop, a galactic merger is neither fleeting nor eternal. It unfolds slowly enough to feel static, yet quickly enough to reshape entire systems. To put this into perspective, consider human history. Modern humans have existed for a few 100,000 years. Recorded history spans only a small fraction of that time. The rise and fall of empires, the development of science, the entire written record of civilization occupies less than a blink on a galactic timescale. If a galactic merger were compressed into a single year, all of recorded human history would occupy less than a single second. This mismatch in scale explains why mergers appear frozen in photographs. When telescopes capture images of interacting galaxies, the structures look dramatic but static. Spiral arms stretch outward. Tidal tails arc into space. Two bright cores hang suspended in apparent tension. Nothing seems to move. That is not because nothing is happening, but because everything is happening too slowly to notice. A single exposure from a telescope might last minutes or hours. Even observations taken years apart show almost no visible change. Compared to the billions of years over which mergers unfold, a human lifetime is effectively zero. This stillness can be misleading. The shapes seen in images are not permanent. They are momentary states in an extremely long process. The fact that they appear fixed says more about the observer than about the event itself. Astronomers understand this by combining observation with modeling, by studying many galaxies caught at different stages of interaction and by simulating their motion over time. They can reconstruct the full sequence. What appears as a frozen sculpture is actually a slow-motion film stretched far beyond human perception. This slowness is essential to why galactic collisions are gentle rather than catastrophic. When change happens gradually, systems can respond smoothly. Stars adjust their orbits little by little. Gas flows redistribute over millions of years. Energy is absorbed, radiated, and dissipated without overwhelming any single component. There is no sudden shock that tears the system apart. In contrast, rapid changes tend to be destructive. On Earth, sudden impacts cause damage precisely because they happen faster than materials can respond. In galaxies, nothing happens quickly. Gravity applies its influence patiently, allowing structures to bend rather than break. This also explains why galaxies can undergo multiple interactions over their lifetimes. A galaxy may pass near another, be distorted, then drift away again, carrying the memory of that encounter in its shape. Later, it may meet another neighbor and be reshaped again. Each interaction layers change upon change without erasing what came before all at once. There is calm logic to this pacing. The universe has no need to hurry. With billions of years available, processes can unfold at speeds that preserve stability while still allowing transformation. This is why even dramatic-looking mergers are survivable. The system has time to adapt. For individual stars within a galaxy, the merger may feel almost irrelevant. Over the course of a star's orbit, the overall gravitational environment changes only slightly. A star completes millions of revolutions while the galaxy slowly shifts around it. From the star's perspective, the universe remains largely the same. Even as the galaxy evolves on a grand scale, this perspective also helps explain why mergers do not feel violent from the inside. There is no single moment of impact, no sudden catastrophe to mark the event. Instead, the night sky would change so slowly that no generation of observers would notice the full transformation. Patterns would shift imperceptibly, new stars would appear, old structures would fade. There is something quietly amusing about the mismatch between scale and perception. The largest collisions in the universe unfold at speeds so slow they resemble stillness. The most dramatic events appear calm precisely because they take their time. Scientific institutions that study galaxy evolution often speak in terms of billions of years because there is no smaller unit that makes sense. When describing mergers, phrases like gradual, extended, and long-lived are not rhetorical choices. They are necessities imposed by scale. Once this sense of time settles in, the entire idea of galactic collision changes character. What might sound like a crash becomes more like a slow blending. What might be imagined as destruction reveals itself as patient rearrangement. This reframing is crucial. Without it, the behavior of galaxies seems puzzling or counterintuitive. With it, their calm resilience becomes inevitable. Space is vast, gravity is gentle, time is abundant. Understanding these timescales allows the listener to slow down as well, to let go of expectations shaped by human speed and human experience, to view the universe not as a place of constant violence, but as a system where even the largest changes unfold with extraordinary patience. Galaxies collide without touching, not only because space is empty, but because time itself is generous. Long before galaxies appear to touch, long before their bright shapes overlap in images, something subtle begins to happen. Two vast systems, each moving through space on its own path, start to feel one another's presence. Nothing visible marks this moment. No boundary is crossed, no edge is breached. Yet, from this point on, neither galaxy is entirely alone. Galaxies are never truly still. They orbit within groups and clusters, drifting along paths shaped by the gravity of their neighbors and the larger structure of the universe. These motions are slow and graceful, but they carry momentum. Each galaxy has direction, speed, and mass, and together these determine how encounters unfold. As two galaxies draw nearer, gravity begins to alter their trajectories. Their paths curve inward, not abruptly but gently, like two dancers adjusting their steps as they circle a shared center. This is the beginning of a merger, though nothing yet looks dramatic. At this stage, the galaxies are still well separated. Their stars remain far apart. The gas clouds drift quietly, but their gravitational fields are already overlapping, and that overlap changes everything. Each galaxy tugs on the other, pulling slightly more strongly on the near side and on the far side. This uneven pull is small at first, but over millions of years it accumulates. Stars begin to drift from their original paths. Gas responds more readily, flowing along newly shaped gravitational contours. The galaxies start to stretch. This stretching marks the first visible sign of interaction. Orbital dynamics play a central role here, though the idea itself can be understood without technical language. When two galaxies approach, they do not fall straight toward each other like dropped stones. Instead, they carry sideways motion inherited from their long journeys through space. This sideways motion causes them to swing past one another, curving into elongated orbits rather than colliding head-on. As they do, something important happens. Energy and momentum are exchanged. Momentum is what keeps a moving object moving in a particular direction. In galactic encounters, momentum is not lost, but it is redistributed. The galaxies pull on each other, changing speed and direction slightly. Some material gains energy and is flung outward. Other material loses energy and sinks deeper into the combined gravitational field. This exchange does not happen all at once. It unfolds gradually as countless stars and gas clouds respond to the changing gravitational environment. The galaxies begin to slow relative to one another, setting the stage for closer encounters in the future. One of the most striking outcomes of this early interaction is the formation of tidal bridges and tails. A tidal bridge is a stream of stars and gas drawn out between two galaxies, connecting them like a luminous thread. It forms as gravity pulls material from one system toward the other, creating a shared structure that spans the space between them. These bridges can stretch for tens or even hundreds of thousands of light years, glowing faintly against the dark. Tidal tails, by contrast, sweep outward. As material gains energy during the encounter, it can be flung far from its original home, tracing long arcs that curve through space. These tails are among the most beautiful features seen in interacting galaxies. Delicate and elongated, shaped by gravity rather than forceful ejection. Despite their dramatic appearance, these structures form quietly. Stars within them are not thrown violently. They are gently redirected, their orbits stretched into new paths that take them far from where they began. Astronomers have observed these features in many real systems. Telescopes operated by space agencies and research observatories have captured pairs of galaxies linked by faint bridges of light and surrounded by sweeping tails. These observations match what simulations predict when gravity is allowed to act patiently over long timescales. What is remarkable is how early these features appear long before the main bodies of galaxies overlap. Their outer regions can already be deeply affected. The visible interaction begins not at the center, but at the edges, where gravity's differential pull is most effective. This early phase of a merger still feels calm. From within a galaxy, the changes would be subtle. Stars would follow slightly altered paths, gas would drift inward or outward a little more readily than before. There would be no sudden disruption, no sense of impact, yet from a cosmic perspective, the commitment has been made. Once galaxies enter this gravitational dance, escape becomes difficult. Each close pass robs them of a little orbital energy, binding them more tightly together. What begins as a near miss becomes over time a drawn-out embrace. There's gentle irony in calling this stage first contact. Nothing touches, no surfaces meet. The interaction is entirely mediated by gravity reaching across space. Contact in this context means influence rather than impact. This redefinition is essential. Without it, the early stages of a merger seem uneventful or incomplete. With it, they reveal themselves as the foundation on which everything else is built. The formation of bridges and tails is not decorative. These structures carry information about the galaxy's masses, their trajectories, and their past motion. Astronomers can study their shapes to infer how the encounter unfolded. Much like reading the wake behind a moving boat, even at this stage, the invisible components play a major role. Dark matter halos overlap and guide the redistribution of visible material. Gas responds more readily than stars, beginning to flow along the changing gravitational landscape. Stars, though slower to react, still feel the pull, their orbits subtly reshaped. All of this happens before any dramatic overlap of luminous disks. The galaxies remain recognizable as separate systems, yet they are no longer independent. There is something quietly elegant about this beginning. No fireworks announce it, no clear boundary marks the transition. Interaction emerges gradually, written into the motion of countless stars responding to a shared gravitational field. Understanding this phase helps explain why galactic mergers feel inevitable rather than violent. They do not begin with a crash. They begin with a conversation carried out through gravity, unfolding slowly as two massive systems start to acknowledge each other's presence. By the time the galaxies appear close together in images, much of the work has already been done. Orbits have shifted. Material has been redistributed. The path forward has been shaped by choices made over millions of years. First contact, then, is less a moment than a process. It is the point at which separation gives way to interaction, not through touch, but through gravity's long reach. From here on, the galaxies move together, their futures increasingly intertwined, guided by forces that operate patiently across the vast emptiness of space. Part 7 of 12. This is the moment that gives the title its weight, the point where two galaxies appear, unmistakably, to occupy the same space. From a distance, this phase looks dramatic. Bright disks overlap, spiral arms interlace. Two glowing systems seem to merge into one tangled shape. To an eye trained on everyday experience, it looks like a collision in the most familiar sense. Surely something must be breaking. Surely stars must be crashing into stars. And yet almost nothing of the sort is happening. As galaxies pass through one another, their stars continue along their paths largely unharmed. Each star moves according to gravity, tracing an orbit shaped by the combined mass of both galaxies. But even now, even at maximum overlap, the distances between individual stars remain enormous. The visual overlap is misleading. What appears crowded is still mostly empty. To appreciate this, it helps to return to scale. A typical star occupies a region a few million kilometers across. The space between stars, even in overlapping galaxies, is measured in trillions of kilometers. During a merger, the number of stars sharing the same region of space increases, but not nearly enough to eliminate the vast gaps between them. It is not that stars narrowly miss one another. It is that they are never close to begin with. Astronomers can estimate the likelihood of stellar collisions during this phase, and the numbers remain astonishingly small. Even in a full galactic overlap, the chance of any one star directly striking another is so low that it can be ignored for most practical purposes. A galaxy could pass cleanly through another and emerge with nearly all of its stars intact. This is the core resolution of the paradox. Galaxies collide without touching because their stars do not define their volume. Light fills the image, but space fills the structure. The same principle applies to planetary systems. A planetary system is an even smaller target than a star. Planets orbit within regions that are tiny compared to interstellar distances. When stars pass by other stars during a merger, those encounters are typically far too distant to disrupt planetary orbits. The gravitational influence weakens rapidly with distance, and most stellar flybys during a merger occur far outside the region where planets reside. From the perspective of a planet orbiting its star, the passage through another galaxy would likely go unnoticed. The night sky would change gradually. New stars might appear. Familiar patterns would distort over millions of years. But the local gravitational environment would remain stable. There is something quietly comforting in this idea. Even amid the largest rearrangements of cosmic structure, small systems can remain undisturbed. This stability helps dispel one of the most common misconceptions about galactic collisions. Popular descriptions often imagine stars smashing together, planets being flung into space, or entire systems being torn apart. These images are compelling, but they are wrong. The real danger to stars during a merger does not come from impact. It comes from gradual changes in gravitational potential. Orbits can become more elongated. Stars can be redistributed into new regions of the merged galaxy. Some may end up farther from the center than before. Others may drift inward. But these are slow adjustments, not violent expulsions. The difference matters. Destruction implies sudden force. What galaxies experience is long-term reorganization. The stars survive. The system evolves. This is why astronomers studying merging galaxies focus less on collisions and more on dynamics. They track how stellar orbits change, how angular momentum is redistributed, and how energy is exchanged through gravity. The physics involved is subtle, cumulative, and patient. Even when galaxies pass directly through one another, the stars behave like two interpenetrating swarms. They share space without interacting directly, responding instead to the overall gravitational field. Once the overlap phase ends, the stars continue onward, carrying with them the memory of that shared passage in the form of altered orbits. There's also a visual trick at work. When true galaxies overlap, their light adds together. Bright regions stack atop one another, making the system appear denser than it truly is. This can give the impression of crowding where none exists. The eye is fooled by brightness, mistaking luminosity for solidity. In reality, the stars remain isolated points of fusion, scattered across immense volumes. This overlapping phase does have consequences, but they are indirect. Gas clouds collide, compress, and heat, as already described. New stars form. Central regions may become more active, but the stars themselves continue almost unscathed. Even the cores of galaxies, where star densities are higher, rarely see direct collisions. These regions are dense by cosmic standards, but still sparse by human ones. The same principles apply, just on slightly smaller scales. From inside a galaxy, the experience would be anticlimactic. There would be no sudden shockwave, no dramatic flash. Over many millions of years, the sky would slowly transform. Constellations would stretch and twist. New bands of light might appear as gas ignites into star formation. But nothing would announce a moment of impact. The universe does not provide a clear marker for when one galaxy passes through another. There is no before and after in the way human events are defined. The process blurs together, stretched across time. This is perhaps the most counterintuitive lesson of all. The most visually striking phase of a galactic merger is also the least destructive. The moment that looks like a crash is the moment when the fundamental properties of space and scale assert themselves most strongly. Galaxies pass through one another because they can. Space allows it. Gravity guides it. Time stretches it out until violence becomes unnecessary. Astronomical observations reinforce this calm reality. Systems observed mid-overlap often show ordered stellar motion despite their tangled appearance. Simulations that track individual stars confirm that their paths remain smooth and continuous. The physics does not allow for widespread chaos because the conditions for chaos simply are not present. There is a quiet elegance in this resolution. The title promises a paradox, but the universe resolves it without drama. Collisions without touching are not exceptions or oddities. They are the natural outcome of structure, scale, and distance. By the time galaxies visually overlap, the story has already been written by emptiness and gravity. What unfolds is not destruction, but passage. Two vast systems share space, exchange influence, and continue on paths shaped by forces that operate far beyond the reach of intuition. Understanding this phase brings everything together. The emptiness between stars, the reach of gravity, the patience of time, and the subtlety of interaction all converge here. The paradox dissolves, replaced by a picture that is calmer, stranger, and far more satisfying than the idea of a cosmic crash. Galaxies collide without touching, not because something prevents impact, but because at this scale, impact is simply not how the universe works. Part 8 of 12. When galaxies pass through one another, the absence of destruction does not mean the absence of change. What follows the overlap is a long period of reshaping where gravity continues its work, not by breaking structures apart, but by gently pulling them into new forms. The result is distortion rather than devastation, transformation rather than collapse. At first glance, the shapes of interacting galaxies can look chaotic. Spiral arms appear stretched and twisted, disks bend out of alignment, bright cores drift away from their original centers. Yet beneath this apparent disorder lies a consistent pattern shaped by tidal forces acting patiently over time. Tidal stretching is the same process that began when the galaxies first approached, but now it operates across the full extent of both systems. As gravity pulls unevenly on different regions, material responds according to how tightly it is bound. Loosely held stars and gas in the outer regions are the first to be drawn out, forming elongated arms and sweeping arcs that extend far into space. These features are not signs of damage, they are signatures of motion. Spiral arms, once neatly wrapped around galactic centers, can be pulled into longer, thinner structures. In some cases, they stretch so far that they detach visually, becoming tidal tails that trace the galaxy's path through space. These tails can contain billions of stars and vast amounts of gas, yet they remain gravitationally connected to the system, slowly evolving rather than dispersing. Galactic disks also respond to these forces. Rather than shattering, they warp. The flat plane of stars and gas bends upward or downward, forming subtle curves that ripple across the structure. From certain angles, these warps are barely noticeable. From others, they become striking, revealing the three-dimensional nature of the interaction. Even the central regions of galaxies can shift. The dense core, often containing a supermassive black hole, may become displaced from the geometric center of the visible structure. This does not mean the core has been knocked loose. Instead, it reflects changes in the overall mass distribution as stars and gas are redistributed by gravity. These distortions develop slowly. A warped disk does not snap into place. An elongated arm does not form overnight. Each change emerges from countless small adjustments as individual stars alter their orbits slightly in response to a changing gravitational field. Over millions of years, these small changes add up to large-scale reshaping. What is remarkable is how resilient galaxies are throughout this process. Despite their altered appearance, interacting galaxies remain coherent systems. Stars continue to orbit. Gas continues to flow. Even dramatic distortions rarely result in material being permanently lost. Much of what is drawn outward eventually falls back in, contributing to the final shape of the merged galaxy. This resilience is evident in both observation and simulation. Researchers working with space agencies such as NASA and ESA have used detailed computer models to follow galactic mergers from start to finish. These simulations track millions of particles representing stars, gas, and dark matter, allowing gravity to act naturally across vast spans of time. Again and again, the results show the same pattern. Galaxies stretch, twist, and deform, but they do not disintegrate. The simulations match what telescopes observe. Systems captured at different stages of interaction display the predicted features, from gently warped disks to spectacular tidal tails. The agreement between model and observation reinforces the idea that distortion is the expected outcome, not destruction. There is an important reason why galaxies respond this way. They are not rigid objects. They are collections of orbiting material held together by gravity. When that gravitational environment changes, the material adjusts smoothly rather than fracturing. Flexibility is built into the structure. This flexibility stands in sharp contrast to cinematic portrayals of cosmic collisions. Popular images often show galaxies exploding into clouds of debris or collapsing into chaos. In reality, there is no mechanism for such sudden ruin. The energies involved are spread across enormous volumes and timescales, allowing systems to adapt. The humor, if it can be called that, lies in how misleading the visuals can be. A galaxy with twisted arms and stretched tails looks wounded, yet it is functioning exactly as physics predicts. What appears broken is simply in transition. These distorted shapes are temporary, though they can persist for hundreds of millions of years. Over time, gravity continues to smooth out irregularities, orbits become more random, distinct features blur together. Eventually, the system settles into a new equilibrium, often quite different from its original form. In many cases, repeated stretching and reshaping erases the orderly structure of spiral galaxies, leading to smoother, rounder systems. The elongated arms fall back inward, warps relax. The The final result may be an elliptical galaxy supported not by rotation, but by the collective motion of stars in many directions. Even then, the history of interaction remains written into the system: subtle variations in star motion, faint shells of stars far from the center, and lingering streams of material all tell the story of past encounters. The galaxy carries its distortions as memories rather than scars. From the inside, this entire process would feel uneventful. Stars would continue their long orbits. The changes would be too slow to notice within any single lifetime. There would be no sense of collapse or catastrophe, only a gradual rearrangement of the sky. Understanding this phase is essential to replacing the idea of cosmic violence with one of cosmic adaptation. Galaxies are not fragile. They are robust, flexible structures shaped by forces that act slowly and persistently. Distortion is how gravity expresses itself when given enough time. It stretches rather than breaks, reshapes rather than destroys. In galactic mergers, this gentle persistence is what allows enormous systems to change without falling apart. By focusing on transformation instead of destruction, the behavior of galaxies becomes easier to understand and far more interesting. The universe does not rely on sudden shocks to evolve. It relies on patience, scale, and the quiet power of gravity working over immense spans of time. In this light, the twisted shapes of interacting galaxies are not signs of chaos. They are evidence of a process unfolding exactly as it should, a reminder that even the largest changes in the universe are carried out with remarkable restraint. Part 9 of 12. After galaxies pass through one another and their shapes begin to stretch and settle, something quietly remarkable often follows. In the wake of distortion and rearrangement, new light begins to appear. Not from explosions or destruction, but from creation. Galactic mergers have a reputation for triggering bursts of star formation, and this reputation is well earned. For a time, these systems can produce new stars at rates far higher than those seen in calmer, isolated galaxies. This increase is temporary, but while it lasts, it can transform the appearance and future of the merged system. The reason lies not in the stars themselves, but in the behavior of gas. As described earlier, gas is the component of a galaxy that truly interacts during a merger. When galaxies overlap, gas clouds compress, slow down, and heat up. Over time, much of this gas is driven into denser regions, especially toward the inner parts of the system. Gravity becomes more effective where gas piles up, and conditions shift in a crucial way. Star formation begins with collapse. Under normal circumstances, large clouds of gas can drift for millions of years without forming stars. Internal motion, heat, and turbulence provide enough pressure to resist gravity's pull. A merger changes that balance. Compression increases density. Motion becomes chaotic. Shock waves ripple through clouds, dissipating energy that once supported them. As pressure support weakens, gravity gains the upper hand. Parts of the gas cloud begin to contract. The contraction is not smooth or uniform. Instead, it fragments. Dense knots form within the cloud, each one pulling in more material as it grows. Over time, these knots become hot enough at their centers to ignite nuclear fusion. A star is born. This process happens on scales far smaller than a galaxy, but it is the galactic merger that sets it in motion. By funneling gas into dense regions and stripping away stabilizing motion, the interaction creates ideal conditions for collapse. The result is a starburst. Starburst regions are areas where stars form rapidly and in large numbers. They can shine brightly in blue and ultraviolet light, dominated by young, massive stars that burn hot and fast. These regions often appear clumped along distorted arms in compressed rings or near galactic centers where gas has accumulated most strongly. Observations from major astronomical observatories have repeatedly shown this pattern. Merging galaxies often glow with clusters of young stars, their light piercing through surrounding dust. At wavelengths invisible to the human eye, these systems radiate intensely, revealing energetic processes tied directly to recent star formation. Yet this creative phase carries the seeds of its own ending. Young stars are not quiet residents of their birthplaces. Massive stars in particular release enormous amounts of energy. They emit intense radiation that heats nearby gas. They drive powerful stellar winds that push material outward. Some end their lives as supernovae, releasing sudden bursts of energy that can tear through surrounding clouds. These feedback processes act as a kind of regulation. As new stars form, they begin to disrupt the very gas that created them. Heating raises pressure, winds carve out cavities, shockwaves stir turbulence back into the environment. Over time, this activity can halt further collapse, slowing or even shutting down star formation in that region. This is why starbursts do not last forever. Even in the most active mergers, the surge of star formation is temporary, typically lasting tens or hundreds of millions of years. Once the gas is consumed, heated, or dispersed, the system settles into a quieter state. Star formation continues at a lower rate, or in some cases becomes scarce altogether. There's a delicate balance at work here. Mergers concentrate gas and trigger collapse, but feedback ensures that the process does not run away indefinitely. Creation and suppression are tightly linked, each shaping the other. This interplay has lasting consequences for the merged galaxy. The burst of star formation enriches the system with heavy elements. Young stars fuse lighter elements into heavier ones, and when they die, those elements are returned to the surrounding gas. This chemical enrichment affects future generations of stars, planets, and potentially even life. In this sense, mergers act as engines of cosmic recycling. The distribution of stars also changes. Many of the newly formed stars end up in dense clusters, some of which may remain bound for billions of years. Others disperse into the broader galaxy, contributing to a smoother, more uniform stellar population. In some cases, repeated bursts of star formation during multiple encounters can exhaust much of a galaxy's cold gas. When this happens, the galaxy transitions into a quieter phase of its life, dominated by older stars and little new formation. This is one pathway by which galaxies evolve from active star-forming systems into more passive ones. There is a subtle contrast worth noting. While mergers are often associated with intense activity, they do not create stars everywhere. The increase is localized, shaped by where gas flows and accumulates. Vast regions of the galaxy may remain relatively unchanged, continuing their slow evolution, or pockets of brilliance flare and fade. From the inside of such a system, the changes would still feel gentle. Over millions of years, the sky would brighten in certain regions as clusters of young stars appear. Nebulae would glow more intensely. Over even longer timescales, those bright stars would age and dim, blending into the background as new generations take their place elsewhere. The humor, if there is any, lies in how unassuming the trigger is. A merger does not smash stars together to create new ones. It simply nudges gas into the right conditions and then lets gravity do what it does best. This creative aftermath reinforces an important theme. Galactic collisions are not purely destructive or transformative in a negative sense. They are part of a cycle. Interaction leads to compression. Compression leads to creation. Creation leads to feedback and balance. In this way, mergers contribute to the long-term evolution of galaxies across the universe. They help explain why star formation was more common in the distant past when mergers were more frequent. They also help explain why many galaxies today are quieter, having already undergone these intense phases earlier in their histories. Understanding star formation in the aftermath of a merger completes another piece of the puzzle. The same processes that allow galaxies to pass through one another without touching also allow them to renew themselves. Emptiness and gravity make gentle interaction possible. Gas turns that interaction into light. Creation emerges not from collision in the everyday sense, but from compression, patience, and time. The aftermath of a merger is not a graveyard of broken stars. It is often a nursery, briefly luminous, quietly shaping the next chapter in a galaxy's long life. Part 10 of 12. As galaxies reshape and settle after their long passage through one another, attention naturally drifts inward toward the densest regions at their centers. Here, buried deep within the gravitational heart of each galaxy, lies an object that seems to promise drama: a supermassive black hole. These black holes are extreme by any standard. Each contains millions or billions of times the mass of the Sun, compressed into a region smaller than a planetary system. The gravity governs the motion of stars and gas in the central core, and their activity can influence an entire galaxy. It is tempting then to imagine that when galaxies merge, their central black holes must rush together in a violent finale. The reality once again is quieter and far more patient. When two galaxies begin to merge, their central black holes do not immediately meet. At first, each black hole continues to sit near the center of its own stellar population, surrounded by stars and gas that move with it. As the galaxies distort and overlap, these cores drift closer together, but they do so slowly, carried along by the mass around them rather than plunging directly inward. The journey of a black hole during a merger is shaped by its surroundings. As a galaxy moves through another, its stars and gas experience gravitational drag. This process, known informally as dynamical friction, acts like a gradual braking force. The black hole embedded within its dense stellar core loses orbital energy over time and spirals inward toward the center of the newly forming system. This does not happen quickly. It can take hundreds of millions or even billions of years. For long periods, the merged galaxy may contain not one, but two supermassive black holes orbiting each other at a respectful distance. They form what astronomers call a black hole pair, or binary. Though even here the word pair should not suggest closeness by human standards. The separation between them can be measured in light years, with vast numbers of stars passing between them undisturbed. During this phase, the black holes are not colliding. They're dancing. Their orbits gradually shrink as they interact with surrounding stars and gas. Each close pass transfers a tiny amount of energy outward, allowing the pair to move closer together. This process is slow and inefficient, especially once the black holes reach separations smaller than the surrounding stellar environment can easily influence. This leads to an important clarification. Black hole mergers are not an Auchinleck trend and not an automatic or immediate outcome of galactic mergers. In fact, they are relatively rare events, and when they do occur, they are delayed far beyond the initial collision of the galaxies themselves. Some galaxy mergers may never produce a black hole merger at all. The black holes may remain in wide orbits, or one may be ejected slightly from the center through complex gravitational interactions. The idea of every galactic merger ending in a dramatic black hole collision is a misconception. When black holes do eventually draw very close together, another subtle process takes over. At extremely small separations, the orbiting black holes begin to lose energy not through interactions with stars or gas, but through gravitational waves. These are ripples in space and time itself, predicted by Einstein's general theory of relativity and confirmed through observation. Gravitational waves carry energy away from the system, allowing the black holes to spiral inward more rapidly. This final stage unfolds invisibly, without light, without heat, without impact. Space itself does the work. The detection of gravitational waves by observatories such as LIGO and Virgo has provided direct evidence that black hole mergers occur in the universe. These detections typically involve stellar mass black holes much smaller than the supermassive ones at galactic centers, but the same physical principles apply. For supermassive black holes, the gravitational waves produced would be far lower in frequency, stretching across longer timescales. Detecting them directly remains a challenge, but astronomers are developing methods to search for their subtle signatures using precise measurements of distant objects. Even here, the tone remains calm. A black hole merger is not an explosion. It does not produce light or shock waves that tear galaxies apart. It is a quiet release of energy into the fabric of space and time, brief on cosmic scales, yet gentle compared to popular imagination. Throughout all of this, the surrounding galaxy remains largely unaffected. The merger of two supermassive black holes does not destabilize stars across the system. The influence is confined to the very central region, and even there it manifests as slight changes in motion rather than destruction. Gas near the center can be affected, however, and this is where black holes make their presence known more visibly. As gas flows inward during a galactic merger, some of it can be captured by the central black holes. When this happens, the gas heats up as it spirals inward, releasing energy in the form of radiation. The galaxy's core can brighten dramatically, becoming what astronomers call an active galactic nucleus. These active phases can be powerful, launching jets and winds that push gas outward and regulate further star formation. Yet, even this activity is episodic. It turns on and off as fuel becomes available or is exhausted. It does not represent a permanent or runaway state. There is an understated balance at work. Black holes respond to the merger by moving inwards slowly. They influence their surroundings by shaping gas flow and energy release, but they do not dominate the process. They are participants, not protagonists. This perspective is important because black holes often attract outsized attention. Their name alone suggests catastrophe. In reality, they are governed by the same principles of gravity, scale, and time that shape everything else in the universe. From a broader view, the behavior of central black holes during mergers reinforces a recurring theme. Even the most extreme objects follow the same calm rules. Change happens gradually. Outcomes are delayed. Influence spreads quietly rather than violently. From within a galaxy, the presence of two central black holes would not announce itself dramatically. Stars would continue to orbit. The sky would remain stable. Only over immense spans of time would subtle shifts accumulate, guiding the system toward a new equilibrium. There is also a gentle irony here. The most massive compact objects in the universe are among the slowest to complete their mergers. Their gravity is immense, yet the distances involved and the need to shed energy make their union a drawn-out affair. Understanding this helps place black holes back into context. They are extraordinary, but they do not override the broader behavior of galaxies. They fit into it. By narrowing focus from the full galactic scale to the central regions, the picture becomes clearer rather than more dramatic. The same principles apply everywhere. Emptiness prevents collisions. Gravity enables interaction. Time smooths change. Even at the core of a merging galaxy, where mass and energy are concentrated, the universe resists sudden endings. Supermassive black holes approach one another slowly, guided by their surroundings, releasing their energy not in fire or impact, but in faint ripples that pass silently through space. This calm conclusion to what might seem like the most extreme outcome completes another part of the story. Galactic mergers do not culminate in cosmic catastrophes. They culminate in quiet rearrangements. Even at their very centers, the universe, it seems, prefers patience over spectacle. Part 11 of 12. Even when black holes are involved, after the long approach, the overlap, the stretching, and the bursts of new stars, the merger enters its quietest phase. The drama fades, not because nothing is happening, but because the system is finally settling. Two galaxies that once moved independently now behave as a single structure, bound together by a shared gravitational center. This settling process takes time. There is no clear moment when two galaxies officially become one. Instead, their identities blur gradually as stars, gas, and dark matter redistribute themselves into a new balance. Orbits that once traced distinct paths around separate centers now belong to a combined gravitational field. At this stage, the most obvious changes are no longer sudden or dramatic. They are smoothing processes. Stars that were once arranged in neat rotating disks begin to move in more varied directions. Some still follow roughly circular paths, but many are scattered into elongated or tilted orbits. Over hundreds of millions of years, these motions mix together, erasing the ordered patterns that once defined spiral structure. This mixing is known as dynamical relaxation. Dynamical relaxation is not a single event, but a long process through which a system redistributes energy and momentum among its components. As stars pass through regions of varying gravitational strength, their orbits change slightly. Each interaction is small, but over time the cumulative effect is significant. The result is a loss of memory. The galaxy gradually forgets how it was assembled. Spiral arms fade, clear disks dissolve. What remains is a smoother, rounder distribution of stars, supported not by rotation in a single plane, but by the collective motion of stars in many directions. This is why many major mergers produce elliptical galaxies. Elliptical galaxies lack the obvious spiral arms and flat disks seen in spiral systems. Instead, they appear as smooth, rounded, or elongated shapes, with stars moving on a wide variety of orbits. The structure reflects the history of mixing and relaxation rather than orderly rotation. In a merger between galaxies of similar size, the disruption is often strong enough to destroy the original disks entirely. The rotational patterns that once held spiral arms in place are scrambled. Without a dominant disk of cold gas to reform the structure, the galaxy settles into an elliptical form. This outcome is not guaranteed. Mergers involving very unequal masses or systems rich in gas can produce different results. In some cases, a disk can reform after the merger, especially if fresh gas continues to flow into the system. But for many large mergers, the elliptical shape is the natural conclusion. The transition feels dramatic when viewed across billions of years, yet it remains calm on any shorter timescale. Stars are not flung violently into space. They are reassigned to new roles within the combined system. Some end up closer to the center. Others occupy the extended outer regions. A few may form faint shells or streams that linger far from the core subtle traces of the merger's past. Gas behaves differently during the settling phase. Much of it has already been consumed by star formation or heated by feedback processes. What remains may sink toward the center, contribute to residual star formation, or be expelled into the surrounding environment. The final galaxy often contains far less cold gas than its progenitors. This change has long-term consequences. With less gas available, star formation slows. The galaxy begins to age. Its light becomes dominated by older, redder stars. The bright blue glow of starburst regions fades, replaced by a steadier, softer illumination. From a distance, the galaxy now looks calm and mature. Its turbulent youth is written only in subtle details, visible to careful observation, but invisible to casual glance. This settling phase also marks the end of the merger as a distinct event. From here on, the galaxy evolves as a single system, responding to its environment, accreting small companions, or drifting quietly through space. The long interaction narrative resolves into stability. There is something quietly satisfying about this conclusion. Despite all the stretching, overlap and change, the galaxy does not collapse into chaos. It does not shatter. It finds a new equilibrium. Gravity, having driven the interaction, now smooths the result. The idea of loss is central here, but it is a specific kind of loss. What disappears is not matter, but structure. The original patterns that defined each galaxy give way to something simpler and more uniform. The system trades complexity of form for stability of motion. This trade is a common theme in physics. Systems tend towards states where energy is distributed more evenly. In galaxies, this means stars moving in many directions rather than marching in neat ordered paths. There is gentle humor in how understated this ending is. After billions of years of interaction, the final result is not a spectacular finale, but a quiet settling. Two galaxies become one, not through a climactic moment, but through patience. From the inside, the transition would be almost impossible to notice. No observer would see the moment when individuality was lost. The sky would change slowly. Over countless generations, familiar patterns would blur and fade. New constellations would emerge, not by design, but by drift. Scientific observations support this picture. Surveys of galaxies across the universe show a wide range of shapes and structures reflecting different histories. Elliptical galaxies tend to be more common in dense environments where mergers are frequent. Spiral galaxies are more common in quieter regions where interactions are rare. The correlation tells the same story again and again. The universe remembers its past through structure. Yet even as structure fades, the galaxy remains alive. Stars continue to shine. Planets continue to orbit. The system persists, reshaped but intact. This structural conclusion brings closure to the merger process itself. The long sequence of approach, overlap, distortion, and creation resolves into a single stable form. The collision without touching has run its course. What remains is a reminder of how the universe handles change, not with sudden endings, but with gradual blending, not with destruction, but with rearrangement. Two galaxies become one, not because one conquers the other, but because gravity allows them to share space, exchange motion, and eventually settle into a common rhythm. The process is slow, subtle, and deeply consistent with the calm logic that governs everything on the larger scales. By the time the merger is complete, the drama is long past. What endures is a new galaxy quietly carrying the combined history of its predecessors, moving forward through space as a single unified system. Part 12 of 12. Among all the distant mergers scattered across the universe, there is one that feels unusually personal. It involves the galaxy that contains every star visible in the night sky, and a neighboring system already familiar to astronomers for centuries. Far in the future, the Milky Way and the Andromeda galaxy will begin a long, slow encounter of their own. This future merger is not speculation. It is a measured prediction grounded in careful observation of motion across space. Astronomers have tracked Andromeda's position and velocity with increasing precision, and the conclusion is clear. The two galaxies are moving toward one another, drawn together by gravity, destined to interact. The timescale, however, is reassuringly vast. Current estimates place the first close approach several billion years in the future. The full merger will take even longer, unfolding across spans of time that far exceed human history. Nothing about this event is sudden. Nothing about it is urgent. The knowledge comes in large part from detailed measurements of stellar motion made by the Gaia mission, by mapping the positions and velocities of more than 1 billion stars within the Milky Way. Gaia has provided an extraordinarily precise picture of how our galaxy moves through space. Combined with measurements of Andromeda's motion, this data allows astronomers to reconstruct the future paths of both systems. What emerges is not a head-on crash, but a slow gravitational dance. Andromeda is currently more than 2 million light-years away. At that distance, the galaxies already influence one another, but only faintly. Over time, their mutual pull will alter their paths, curving them inward. The first encounter will stretch both galaxies, drawing out tidal features much like those seen in other mergers across the universe. From the outside, the process will look familiar. From the inside, it will feel remarkably calm. One of the most common reactions to hearing about this future collision is concern. Will stars collide? Will planetary systems be disrupted? Will life be threatened? The physics explored throughout this story provides a clear answer. The risk to individual stars is essentially negligible. Even when the Milky Way and Andromeda overlap, the vast distances between stars remain. The chance of any given star colliding with another star is extraordinarily small. The same is true for planetary systems. Planets orbit stars on scales that are tiny compared to interstellar separations. Most stellar flybys during the merger will occur far too distant to disturb planetary orbits. From the perspective of a star like the Sun, the merger would be a slow change in scenery rather than a violent event. Over millions of years, the night sky would transform. Andromeda would grow larger, brighter, and more complex. New streams of stars would appear. Familiar patterns would stretch and fade, but the local environment would remain stable. There is something quietly comforting in this. The future merger reminds us that even events involving entire galaxies do not necessarily threaten the small scales that matter most to individual systems. The universe is structured in such a way that large-scale change does not require small-scale destruction. Gas dynamics will play a more active role, as in all mergers. As the galaxies interact, gas clouds will compress, triggering new waves of star formation. The Milky Way may experience periods of increased stellar birth, especially during close passes. These episodes will be bright and energetic on galactic scales, yet spread across enough time to remain gentle. Eventually, after multiple passes, the two galaxies will settle into a single system. The result is often referred to informally as a new galaxy formed from the combined mass of both. Its structure will depend on how much gas remains and how energy and motion are redistributed during the interaction. Many simulations suggest that the final outcome will resemble a large elliptical galaxy supported by stars moving in many directions rather than a thin rotating disk. The familiar spiral structure of the Milky Way is unlikely to survive intact. But again, This change unfolds slowly. There is no moment when the galaxy suddenly becomes something else. The future Milky Way will not notice the transition in the way a living being notices an event. It will simply continue evolving. It is also worth noting that the Sun itself won't be present to witness the merger. Long before the galaxies interact, the Sun will exhaust its nuclear fuel and change state. The story of the merger belongs to distant future generations of stars and planets, not to the present sky. This perspective helps keep the event grounded. The merger is real, but it is not a threat. It is part of the normal life cycle of galaxies in groups like our own. The local group, which contains the Milky Way, Andromeda, and dozens of smaller galaxies, is a gravitationally bound family. Over time, its members interact, merge, and rearrange. The future collision is simply the largest chapter in a much longer story that has already unfolded many times. There is also a quiet symmetry in applying everything learned so far to a familiar system. The emptiness between stars, the reach of gravity, the role of dark matter halos, the patience of time. All the principles explored in distant galaxies apply just as clearly here. Nothing special or exceptional happens because the galaxies involved are our own. The same rules govern all systems without favor or urgency. From an imaginative standpoint, the future merger offers a gentle exercise in perspective. One can picture the night skies slowly changing generation after generation, Andromeda's core growing more detailed, streams of stars arcing across the darkness, new constellations forming not by chance, but by drift. There is even room for light humor in this cosmic inevitability. The Milky Way is not being invaded. It is participating in a long-scheduled interaction following gravitational agreements set billions of years ago. No alarms are necessary. No countdown clocks apply. Astronomers studying this future event do so not out of concern, but out of curiosity. It provides a nearby laboratory for understanding mergers in general. By knowing what will happen here, scientists can test their models against a real, evolving system, even if the full process will never be observed directly. In that sense, the future collision is already valuable. It connects abstract theory to a concrete example. It anchors the vast ideas of galactic evolution to a place that feels close and familiar. By bringing the story home, the merger between the Milky Way and Andromeda reinforces the central message. Galactic collisions are not catastrophic impacts. They are long conversations carried out through gravity and time. When our galaxy eventually passes through another without touching, it will do so quietly, patiently, and without harm to the stars that call it home. The universe does not rush its changes, even when entire galaxies are involved. Understanding this allows the future to feel less threatening and more instructive. The Milky Way's fate is not one of destruction, but of transformation, unfolding slowly, predictably, and with remarkable calm.